Well, greetings, mathletes, and welcome. Today we're going to be taking a look at function transformations. And function transformations are a way to either move functions around up and down or change their shape, stretch them, or reflect them, things like that. So there's three transformations we're going to be looking at. We have translations, which is not changing the shape, but moving where the function is. Then there are reflections, which is giving you a mirror image of the function. And just depending on which way you reflect it, you get different things. And then finally, we have the last category. And most people aren't familiar with this word, but I like to use it anyway. They're called affine transformations. And these are your stretches and compressions. So like in trig, when we saw the trig functions get compressed or stretched, or we saw the altitude of a function, the amplitude of a function change, those are affine transformations. Okay, so I just like to use the word affine because it includes both stretches and compressions, but we will draw a distinction between the two. Okay, so looking at that, we have, let's turn the brush on. We have our transformations. Now, the first one is a translation. Right? There's two types of translations. A vertical translation, which is real straightforward. I should actually add this: transformations of f of x, right? So you're going to take the function f of x and do something with it. So I have two types. This could happen two different ways, where y is equal to f of x plus some constant. Okay, so adding a constant to a function basically will move that function up or down depending if that constant is positive or negative. The other one changes, let's see here, that would be y equals f of x minus c, right? And notice this one is affecting the x, and this one moves you left and right. Okay, so this is up, down, and this is left, right. Okay, then there are reflections. Okay, so a reflection is exactly what you think about, a mirror. So let's see here. Let's see here. If I'm going to reflect it in an up and down manner, which is across the x-axis, but it's up and down, I would take f of x, and if I wanted to flip it upside down, I put a minus in front of it, right? So this is an up-down. That's an up-down reflection. And then if I want a left-right reflection, I change the x, right? I put the negative on the x. And this is actually a common theme. I want to point this out. If you look at these two, the up-down reflections both do things to the outside of the function, right? And remember, the outside of the function, your f of x is your y. So if you're changing f of x from the outside, like adding something to the outside of the function or multiplying something like a negative to the outside of a function, what you're doing is you're changing the y value. And if you change y values, that's an up-down change of some sort. Over here, you notice here I'm subtracting something from the x, and here I'm multiplying the x by something. So I'm affecting the x. And in both of these cases, changes in x result in a left-right change. Okay, so if you're changing the outside of the function, it's going to be a change in some up and down manner. If you're altering the inside of a function, you're changing the x value, which means you are altering it in a left or right kind of fashion. Really, think vertically and horizontally, right? If it's up down, that's a vertical change of some sort, and if it's left right, that's a horizontal change of some sort. Now, the last one, the affine transformations, actually do follow much the same thing, but it's multiplying a constant toward on the outside. So the affine would look something like this. So if I wanted to stretch or compress in a vertical fashion, so this is stretching things upwards or pushing things downwards, I multiply the outside of the function, right? So that's an up or down stretch. And if I want to stretch or compress in a horizontal fashion, I alter the inside of the function. Okay, so again, this is the stretch in an up down. This is the up down, and this is left right. So you notice it follows a theme here. Now, some interesting things happen when we start taking a look at these, particularly with the affine transformations. But it's most apparent in the transformations of the x value. When you transform things in the x direction, they do the opposite of what you expect them to do. As well, I suppose all of our x's do that, right? I mean, who hasn't had an x who does the opposite of what we expect? Anyways, I just lost my train of thought. Let me try this again. Okay, so yeah, if I'm subtracting c, right? If this was like an x minus 2, your expectation is that it goes to the left because that's a minus 2, but it does not. It actually goes to the right. All the things in the y direction, though, go exactly as expected. And so we'll take a look at those things. Now, this function over here on the side is so that we can look at examples of how this works without getting locked into predetermined functions like x squared and things like that. We're actually going to break this off and look at those things a little bit later. So I just want to go through and look at these transformations, these 6 transformations, and see how they affect this function. Okay, so we'll just take them one at a time. So let me go ahead and clear this off here. Why is this not working? There we go. Oh, delete that. Let's just do the eraser. Okay. Hi. Okay. So, almost forgot to turn the pen back on. So if this is our function f of x, actually, you know what? I'm going to put that elsewhere so that we don't accidentally stomp over the f of x, because we're going to use this for graphing. Okay, so let's look at our first transformation. Let's say we have y is equal to f of x minus 2. Now, keep in mind, with all of these points here, these are inputs and outputs. So like this point right here, this point 0, 0 tells you that f of 0 is equal to 0. Well, if I go over here and plug that in, right, this becomes a 0, and now I have 0 minus 2, which is now a negative 2. Which means that this point here drops down to negative 2. I'm going to change the color here so it stands out. Probably should have made my graph just a little bit bigger. That's okay. So this minus 2 here took this point and dropped it down 2. Right? Okay, well, let's see what it does to the next point. If I look at the next point, if I plug in 2, I get 2, but this minus 2, right, if I have y is equal to f of 2 minus 2, f of 2, it says right there, it says f of 2 is 2. So this is 2 minus 2, which is 0. So this one also drops down 2 to here, right? And so this line here now becomes this line here. Okay, well, the same thing happens with all of the points. Each one, you compute it, and then you subtract 2 from it. Notice it's only changing y values. right? This point right here, the x value is still 0. This point right here, the x value is still 2, but the y value is changing. So if I look at the next point, it's going to drop down 2 again, which puts it, let's see, you go 1, 2. That's our next point. So here's what I want you to do. We've mapped the first 3 points. Just take a moment and pause the video and see if you can finish the graph with what we've covered so far. And then we'll finish it up together. But go ahead and pause it right here. Did you pause it? Okay, I'm assuming that you paused it here. And so let's go ahead and take a look at the rest of this. So again, this one's going to drop down 2. So that one's going to be here. This point is going to drop down to here. So let's see here. We got this and this. And it's not a perfect graph that I drew in the first place, but okay. Clearly. And then this guy. So you notice, this is a rigid transformation, meaning that the shape doesn't change. It just drops the thing straight down 2, right? That wasn't too bad, was it? Right? So you can do that with any function. Even if it's one of these, like x squared, if you have an x squared minus 2, it takes the whole parabola and just drops it straight down 2. So that's what that one does. Now let's go ahead and take a look at the next transformation here. Let's see here. Okay, so we've looked at the vertical shift. Now I want to look at y equals f of x minus 2. Okay, so now this is one of the weird ones, because what it ends up doing is it shifts things in the opposite direction you expect, right? If you plug in 0 into f of x, right, if you just try to do the same strategies we did before, if we have y equals f of 0 minus 2, now we have f of negative 2. Well, that's not a defined quantity. We have no values over here at negative 2, right? The function doesn't even exist there. So it doesn't quite make sense to do things that way. What you end up doing is realizing what you have to plug in for x to make it act like things you... Oops, that's not what I wanted. Let's try this one more time. I was trying to do this. There, that's what I'm trying to do. Okay, what you have to do is try to figure out, what does x have to be to make it behave like a 0, right? For this whole inside piece to behave like a 0. And if I want it to behave like a 0, x better be 2, right? So f of 2 is what's going to give me, or yeah, I guess if I plug 2 in here, now I have f of 0, and that gives me a 0. But notice where 2 is. 2 is over here. So that's not this point moving down, it's this point moving over. And you notice it moved to the right. It did not move to the left. So when you affect your x's, they do the opposite, right? They go the opposite of what it looks like. So the opposite of the sign is the direction that you move. And the same thing here. If I wanted to see what happens here, well, what does x have to be for the inside of this, for the input of this function to be a 2? Well, x had better be a 4, right? So if I plug in f of 4, if I plug in 4 into this new function, I end up with f of 2 again. And f of 2, let's see, we can read it off right here. F of 2 is 2. So up here at 4 now, we're at 2. So again, this one moved 2 to the right, and we actually have this guy moving across here now. And if we keep going, everybody moves 2 to the right. So this 0.31 now moves to here. This 0.41 now moves to here. And you end up just piecing it together from that. 5.3 will move to here. And then 6, 0 moves to here. You notice I'm not even looking at the numbers. I'm just counting the spaces. Right? So everything moves to the right. And again, it's the opposite direction of what you would expect. Right? So if this was x plus 2, it would move, the whole thing would move 2 to the left. And so you just end up moving it point by point right over. It's the exact same shape. It's just translated over. Or in the previous case, it was translated up or down. I think we went down last time. So you need to be able to keep track of those. Now, let's go ahead and look at the next example here. So for the next two here, we're going to need a bigger graph. So I went ahead and grabbed one of those. Probably should have started out with this, but that's okay. Now, the next ones we're looking at are the reflections. I don't know why I always want to misspell that, but so we're talking about reflections. So those look like, well, let's start with the vertical reflection, right? The one it's the up and down reflection. So if we look at y is equal to negative f of x, okay? So let's think about what that means. F of x is a y value anyways. So by throwing a negative in front of it, that means we're changing all of our y values to their opposites. So if I have a negative y value, it becomes positive. If I have a positive y value, it becomes negative. And well, this one's actually kind of nice because they're all positive y values to start out with. So we can just change all of the y values to negative ones and go from there. Notice zeros don't move, right? If the y value is 0, if you make it negative, it's still 0. So these points here on the ends are going to be the same. This one, if I change this y value to a negative 2, it just maps it down to here, right? If I change this y value, this 1, to a negative 1, it maps it down to here. And I can map all the points across the x-axis. All right, so that one's 3, so that comes down to here. And then this guy stays the same. And so all we have to do is connect the dots now. Let's try to get the right angle on this. Right, and just connect everybody up. And we'll see, it really does look like a reflection. What is interesting is that almost all of geometry can be taken care of just using these types of transformations. I just find that absolutely fascinating. But nonetheless, okay, so that is our vertical reflection. And then we have our horizontal reflection, right? And that's when we make the negative in front of the x. Let's just change the color so it stands out. Let's see how this one looks. That was not too bad. Okay, so we're looking at y is equal to f of negative 8. There we go. So f of negative x. Now, again, if we start thinking about plugging in x values here, we run into problems because as soon as you plug in 2, I have f of negative 2, which is not on the graph. So what ends up happening is for this function to be able to recognize what you're putting into it, it's negative. You have to put in its negative so that this negative switches it back. So if I wanted to evaluate y when x is negative 2, this would be f of negative 2, which makes it f of 2. And since we can just look at the function, f of 2 is equal to 2. So you notice we plugged in a negative 2 to do that, which means that it puts it on this side, right? So that means our first line here actually goes right there. And essentially what it ends up all boiling down to is just change all the x values to their opposites, right? So if it's positive, make it negative. If it's negative, make it positive. And so here we go. So we made the x value here negative 2. We got that. The next one, we need to make this x value negative 3, which puts it there. And here we need to make the x value -4, which puts it there. And then let's see, 5, 3, make the x value -5, which puts it there. Right, we'll go ahead and connect that one in. And lastly, we have the point 6, 0, which turns into -6, 0. So really all I'm doing is changing how the coordinates behave, and it completely changes the graph. In fact, it reflects it. In fact, we can see that right here. If I change x, if I make x negative, it reflects it across the y-axis. And if I make y negative, if I make f of x negative, it reflects it across the x-axis. Right? Okay, so those are reflections. Okay, so now we're going to look at the affine transformations, right? And we'll start with the affine transformation of y, which is a vertical. Excuse me, I almost said the wrong thing. A vertical stretch or compression, right? So again, we have this function is f of x. Let's say we have y equals 2 times f of x. Well, we can just use some logic here. Remember, f of x is your y value. So what this is telling you how to do is find your new y value, right? If you want the new y value, you multiply the old y value by 2, because f of x is the old y value. So let's just look at what that does if I multiply each of these y values by 2. Okay, so let's see here. Let's see, that's 0, 0, that doesn't change. This y value is 2. If I multiply it by 2, that puts it at 4. This y value is at 1. So if I multiply that by 2, that puts me there. This one's also a 1, so I'm going to get the same value. Here we have y value is 3, so if I multiply that by 2, that brings me all the way up to here. And then this guy stays the same again. So our zeros still stay at zeros. And then we just need to connect everything. Now, part of the reason we're doing this with a function that we don't need to compute any of the values is so we can see what the concept is behind it. In the second part of this video, we're going to take a look at some of the functions that we're more familiar with and see what happens to those as well. Okay, so this is our affine transformation. This is this would be a stretch of f of x, right? It's stretching it by a factor of 2. Now, what do you call it? These stretches and compressions are really interesting. If we are talking about vertical, right? If we're talking about a vertical affine transformation, this number that we multiply c times f of x, really what we're going to do, if one of the old coordinates is xy, the new one ends up being x times cy, right? So you just end up multiplying whatever that number is on the outside by your y values and see what happens to them. What that means is that if c is between, well, I guess if it was equal to 0, that'd be a problem because it would just zero everything out. But if c is between 0 and 1, it's a compression. If c is greater than 1, it's a stretch, right? And if c is equal to 1, nothing happens because 1 times anything is itself, and that includes functions. So yeah, in this case, we had 2, which is bigger than 1, so we had a stretch. But had I changed this function to something like, let's do this one in red, y equals 1/2 of f of x, it would cut all of the function values in half. So you'd end up with something that looked like this. Right? And everything would have half the height that it had before. right? So you can change, you can stretch things out, or you can push them down depending on what you pick, right? Now, that is a vertical um, compression or stretch. Let's take a look at what a horizontal one looks like. So let's go ahead and select that. Let's go ahead and kill all that. All right. So we have the last thing we need to talk about today is the horizontal stretches and compressions. So the horizontal stretches and compressions are going to look like y equals f of x, f of c times x, as far as that goes. And let's go ahead and see what happens here. So let's go ahead and start with, because we'll play with values of c basically. We'll start with y is equal to 2 times f of x. Okay, now that is not horizontal. Doggone it. Let's try that again. At least I spotted it. F of x is equal to 2x. There are f of 2x. There we go. Y equals f of 2x. Now, if I go ahead and plug some of these things in, like zero's fine, right? You plug in 0, that means it's f of 0, and we already know f of 0 is 0, right? We can see that. But we start to have a problem here when if I try to plug in 2, because that makes it a 4, and that's over here at 1. And so, we're going to start running into problems. We're going to start getting numbers that aren't on there. And so if I want to know what happens to this point, I have to think, what x value would I plug in here so that this ends up being f of 2 when I'm done, right? And x has to be 1. It ends up being half of what the x value is, right? Because I'm multiplying it by 2, I need to cut the x value in half so that it comes out to the same y value. So that means the x value is now going to be at 1. So that moves it here. What it's doing is it's by putting 2x in there, it's actually cutting all the distances in half. The distances from the y-axis. So it's shortening that distance. This is very similar to in trig. If you remember looking at the period of a function, if you made the coefficient of theta a larger number, it compressed the entire wave function down smaller. And it's doing the same thing here, right? So this one compresses to there. 3, 1, well, we have to cut 3 in half. So that puts it right there in the middle. We can already see this is much more cramped. 4, 1, that puts me at 2. Let's see here. And then 5, 3. So it's still at 5, but 3 is cut. Oh, wait a second. It's still at 3, but 5 is cut in half. So that gives me 2.5. Right, so that puts it here. And then here with the 6, 0, I'm cutting the 6 in half, and that puts it at 3. So that actually compressed this thing by a factor of 2. So it cut it in half when you altered the x value by doubling it. The size of the function cut in half. And basically what's happening is, because you're doubling each x value, when you plug in 1, it's acting like a 2. When you plug in 3, it's acting like a 6, right? And so it gives you the same y values as you go along. Now, again, you run into the same thing as before, where you have this difference whether c is bigger than 1 or less than 1. So if c is greater than 1, we just saw that case, right? It's a compression. And we're going to find that with this next example, that if c is greater than 1, or c is between 0 and 1, right? It's a stretch. Okay, so if I look at y is equal to f of 1/2 x, Well, let's see what you guys can do with it. We'll do the same thing here. You go ahead and pause this and see if you can deduce where all these points move to. So take a minute, um, give it some thought, and see what you can come up with. And then once you think you have an answer, push play, and then we'll compare it. Let's go ahead and push pause. I'm just checking to see if you paused it. Are you working? Okay, so let's go ahead and take a look here. There's my pen. I lost it for a second there. Okay, so let's go ahead and take a look at this guy. I'm going to do this one in red. So now we're cutting the x's in half, right? So the reverse happens. When we multiplied by a number bigger, what it did was it compressed everything. If we multiply it by something smaller, it's going to stretch everything. And that's because, like here, if I want to get f of x to equal 2, right, I would plug in a 2. Well, if I'm cutting that number in half, that means I have to plug in a 4 to make it a 2, right? So you end up having to make these numbers bigger to accommodate. In fact, let me see if I can inch out some of this stuff so it's not competing. Well, it's not going to be perfect. We'll accept it that way. Okay, so 0, 0, it doesn't matter what you multiply or divide 0 by, you still get zeros, right? Here at 2, 2, this now stretches out to 4, right? So the first line here is actually here. Okay, the next one is 3, 1. Now 3, 1, that means I have to jump all the way out to 6 because I'm doubling the 3. Really what you're doing when you stretch and compress in an x direction, you're taking the previous x value and you're dividing it by c. Whether c is big or small, that's what you're doing. You're dividing it by c. So when we change the y values and we stretched and compressed vertically, we multiplied by c. We multiplied the y value by c. With the x values, we divide by c. Okay, so we got that now. And then the next one, let's see here. What's the next one? So that's that. So 4, 1. Oh, that's going to jump out here. 6, 7, 8. Right? You notice it didn't flatten it at all. Everything is still the same height. Right? And so this one was at 5, so that's going to be at 10 now. Right? So 10, 3. And the last one is 6, 0, so that's going to be at 12. Right? And we end up stretching the whole thing out like this. Right? So it just took it and slid everything. It basically just slid everything apart. And again, this is a lot like changing the period in a trig function. In fact, it's the same mathematics. It's just they're not trig functions. That's the only difference here. This is identical mathematics. Everything you do to wavelengths and wave functions to alter them and change them, those are all function transformations. And that's part of the reason that we study them. Because that's really the biggest place they're applied. Okay, now that's a quick review of our function transformations. I know you've seen at least some of these in trig, even if they weren't called transformations when you did it. All of these things were done. For example, when you alter the amplitude of a trig function, what you're doing is a vertical stretch. When you alter the period of a function, what you're doing is a horizontal compression or stretch, right? The trig functions, when you shift them, right, those are vertical translations or horizontal translations. And again, the reflections and stuff. And we usually took care of the reflections using the odd and even function properties, right? Because that tells you what you can do with the negative, so you don't have to mess around with them in painful ways. But we still did all of these things in trig. So in any case, that's your quick review of these. In the next video, this is really kind of part one. The next video is going to include actual like analytic functions, ones that you actually have to work some things out. And we'll just go through examples in the next video so we can try to get a feel of how all these things relate to each other. So that pretty much is it for today. So until next time, folks, keep your pencils and your wits sharp.